Alright, so this is part A of homework 3, where we're going to describe a pipe with 6 different variables and create a dimensional matrix for Buckingham Pi method to create dimensionless numbers, but instead of calculating it manually, we'll use the null space in Python to calculate these three different dimensional groups. So let's first start with a pipe. And the first variable that affects a pipe is the length, L. The second is diameter, D. Third is the velocity of the fluid flowing through. The third is density of the fluid. The fourth is the viscosity of the fluid. Or the fifth is the viscosity of the fluid. And the sixth and the final is the pressure drop, delta P. So the variable first, length, the symbol of L, has dimensions L. And these dimensions are mass, length, time, and their SI units. And the mass is kilograms, length is meters, and time is seconds. So the components of length are just 1 for L. And same for diameter, but the symbol is D. Dimension is only L, which is meters. So it's 0, 1, 0, same. Velocity, symbol is V, and it's meters per second. So length divided by time. So it's 0, 1, -1 because T is in the denominator. Density, which is rho. Density is mass divided by volume, and volume is length cubed. So the components are 1, -3, 0. Viscosity, mu, is mass divided by length times time. So it's 1, -1, -1. And delta P, pressure drop, is mass times length times time squared. So the components are -1, -2. So now we're going to convert this into an array. And we're going to call this array A just for simplicity. And so we're going to do length, diameter, velocity, density, viscosity, pressure drop. And so the rows, or the columns, are the variables, and the rows are MLT. So it's 0, 1, 0 for length, 0, 1, 0 for diameter, 0, 1, -1 for velocity, 1, -3, 0 for density, 1, -1, -1 for viscosity, and 1, -1, -2 for pressure drop. So now we're going to introduce the idea of a null space. So I'm going to copy this, bring it down here. So a null space is a linear algebra topic where you multiply an array to get a property that you desire. And the property that we desire is for everything to equal 0 to get dimensionless number. So this null space is going to have 6 different C's in it. And the 6 different C's are because of the 6 different variables. And then, so this area is the null space. And like I said earlier, it's a linear algebra topic where you can, it's a vector. In this case, it has 6 dimensions. And is used to achieve a certain property. Like, certain property is all the zeros, like I said earlier. And this null space, all these C's there's an infinite amount of C's that there can be. So in this case, going back to the Buckington pi, we have 6 unknowns, which are the 6 different variables, 3 equations, which are the ML and T. So then that gives us 3 variables. So that means we can constrain 3 of the 6, L, D, V, rho, mu, and delta P. So we're going to constrain L, viscosity, length, viscosity, and the pressure drop. So equation 1 is going to be we're going to constrain L to be 0, rho to be 0, and delta P to be 1. And D is we're just gonna label that A, B, and C, because that's what we're gonna calculate in the Python code. Equation 2 is gonna be we're gonna constrain L to be 1, rho to be 0, and delta P to be 0. So C, D, E, F. And like I said earlier, like all the letters A, B, C, D, E, F are going to be calculated in the Python later in the video. And then for this third equation, we're going to constrain L to be 0, P to be 0, or delta P to be 0, and rho to be 1. So then H, I, we're going to label these. And so now we're going to go to the Python code. Alright, so now I'm going on to the Python code to solve for our dimensionless units. So right here I have my notes from earlier that are shared on the side. So first, I'm going to import NumPy as NP and import SciPy as SP. Load. Okay. Alright, now I'm going to put in my array. So the first row M is, well, I'm gonna just denote this actually. So rows are M, L, L, T, and columns are L, V, or LD, V, row, U, and delta P. Okay, so it's 0, 0, 0, 1, 1, 1 for the first one. Second one is 1, 1, 1, negative 3. Can't really see me. Oh, it's too much. Why does it keep adjusting? -3, -1, -1. And the third column is 0, 0, -1, 0, -1, -2. And we're going to put a period here to let it know that that's the end of the code. Alright, perfect. Alright, now let's just make sure it gives it to us correct. No, it does not. Okay, let's get rid of this. Oh, I'm missing a... Alright, now let's see if it gives it to us correct. No, not right still. Okay. Oh. There we go. Okay. So now I'm going to Alright, so now that gave it to us right, I'm just gonna delete it, this new line of code. Right now we're gonna create the null space, ns equals SciPy times linear algebra. And null space A, array A. Alright, and now let's see if it created the null space correct. Yep. Alright. So now solve for C1. Okay, we're gonna take the NumPy times linear algebra, and we're gonna solve for that null space. And the null space, we're gonna change the L, the mu, and the delta P, and these in the array are 0, 4, and 5. And we're gonna a colon, so it goes through the whole array. And for the NumPy times the array, and we're going to change that to, our first equation was 0 for L, 0 for mu, and 1 for P. Oh, I forgot to put the period to let it know that we're stopped. Nope. Okay, there we go. Alright, so now we're going to get the C1 array. Alright, now we're going to do the null space at C1. Alright, so that is giving us okay, well, the light's going out. So L is 0. Oh yeah, so it's -5 to the -17th, so that's like basically 0. For L, length, diameter, same thing, it's basically 0. Velocity is 2. Okay, let's start with delta P, because there's one of that. Rho, or mu, is it's 0, because it's to the -17th. Or mu is 0. Rho is 1, -1. And velocity, density, and length are 0. So then that gives us pi 1 to be delta P over rho, which is the first oh, just kidding. It's rho is -1 and velocity is -2. So rho times a velocity squared, which is the first dimensional number up here. Alright, so now we're going to do the same thing for pi 2. We're basically just going to keep the same thing, but change L to 1, this to L to 1, mu to 0, and delta P to be 0. Gonna run that, rerun this, rerun that. So then that gives us pi 2 equal to L1 times d to the negative 1, diameter to be the negative 1, b to be 0, u also to be 0, and delta P to be 0. So then that gives us pi 2 equaling L over D, which is the second dimensionless number. And now we're going to do the third one. And what we constrained this one to be is L to be 0, rho to be 1, or mu to be 1, and delta P to be 0. I'm gonna rerun this, and rerun this. So then that gives L to be 0, D to be negative 1, rho to be negative 1, mu to be negative 1, or to be 1, and delta P to be 0. Oh, forgot velocity. Okay, do this again. So diameter to be negative 1 times velocity to be negative 1 times rho to be negative 1 times mu to be 1 times delta P to be 0. So then that gives us diameter times velocity times rho, all in the denominator, which is a third dimensionless number. And if we invert this, then it's the third one. This is the inverse of Reynolds number.